So let's go back to theorem 3.4.3 that said that the square of any odd integer has the form 8m plus 1 for some integer m. All right, in this particular one, we're definitely going to have cases, but we're going to have to probably think through exactly what those different cases are going to be. Let's first rewrite this in an if-then format. I'm going to suggest to, and there may be varying ways to write this, but since we want to start with an odd integer, we can start with if x is an odd integer, then x squared has the form 8m plus 1 for some integer m. So if I'm trying to prove this, of course, after the word proof, we're going to write what we're going to assume. So let's say we're going to assume x is an odd integer. All right, now the question is, how can I take that and be able to write x squared in this form here? Now just pretend like this is our scratch paper, and let's say that we've assumed that x is an odd integer, and we just wanted to try to prove this directly, and we didn't know that we had to break this into cases. Okay, well, if x is an odd integer, then that means that I can write it as 2k plus 1. Now, of course, we'll have to write all the details in here. And then if I square it, that would give us 4k squared plus 4k plus 1. Well, the question is, do I have any hope here of being able to write this in the form 8m plus 1? All right, and I think I'm going to say no. All right, so I don't see how to take 8k squared plus 4k plus 1 and write it as 8m plus 1, where m is some integer. Now, just as a reminder, remember how we took numbers and we wrote them into these formats? Well, since I'm aiming for something that has an 8m plus 1 to it, I might want to go with one of these. All right, and I guess my first thought would be, is it possible maybe to go with this one right here? All right, let's see if we get anywhere with that one. So we tried to prove this directly, and it just really didn't help us out. So we're going to try to think about, we could write this using the quotient remainder theorem. We could write this x that we see here as 2 times k, which would be the first case, or x could be 2k plus 1. All right, and that would certainly cover all the different cases that we would have. All right, well, if x is equal to 2k, again, this is my scratch paper, so I would have x squared is equal to 2k squared, and that gives me 4k squared. And so the question is, am I going to be able to take that and write it as something with an 8m plus 1? All right, well, it's not really obvious to me exactly how we would do that. So I don't think the 2k and 2k plus 1 are going to be helpful. So then we back up and we say, okay, well, if this one wasn't helpful, is writing it mod 3 going to be helpful? And I think you can probably see that there's no way to get from a 3 squared to an 8, so I'm going to just go ahead and knock that one off. And I would say that you probably want to think of like factors of whatever the number is. Like we have 8, so think about like 2, 4, and 8. So let's try this one, this mod 4. And we're going to break it into 4 cases. So we're going to have 4q, 4q plus 1, 4q plus 2, and 4q plus 3. And for every case that we have, we'll have to write it as 8m plus 1. Now, I know that this one is going to be helpful, so I'm going to go ahead and just write this as if we were proving this one and we already knew that it was going to help us out. Now, it's the quotient remainder theorem that really tells us that we can write this x in that format. So I'm going to write by the quotient remainder theorem. If you want to say QR, that's fine. I'm going to use THM for theorem for short. By the quotient remainder theorem, we can write an integer as 4k, 4k plus 1, 4k plus 2, or 4k plus 3. All right, so those are my possible situations here. All right, now one other thing that we do know is that x is an odd integer, and so I think you can probably look at this and you can rule a couple of these out. All right, we know that 4k is an even number, so we're going to go ahead and just say we can't really have this one. Also, 4k plus 2 is an even integer, and so those are not going to be anything in our cases. All right, so we're going to look at 4k plus 1 and 4k plus 3. One other thing that I should write here, when we say that we can write it as 4k or 4k plus 1, etc., this is where k is an integer, because I think this will be important later on for us to note that. All right, so we just said that 4k and 4k plus 2 were even, so let's just say because 4k and 4k plus 2 are even, we will not consider these. All right, because remember, we were told that x is an odd integer up here. All right, and so we just have two cases. All right, it could be that x is equal to 4k plus 1. All right, well, if x is 4k plus 1, that is going to imply that x squared is going to be equal to 4k plus 1 squared, which is 16k squared plus 8k plus 1. Now remember, the question is, can we write it in this form that we see up here? Can we write it as 8 times m plus 1? Well, sure we can. We can write, or at least we can write it as 8 times something. We can write this as 8 times 2k squared plus k plus 1. So then the only question is what's in the parentheses right here, is this an integer? And I think you can see that it is. Remember how I told you that k being an integer is going to be important? Well, since we know k is an integer, all we're doing down here is we are just adding and multiplying integers, and so by the closure property, that will be an integer. But we do need to state that. So we'll say by the closure property, two k squared plus k is an integer. And so that's going to be our m value that we were looking for. All right, so we're trying to write it as 8 times m up here. All right, well, just let this be our m. And so we'll just say if we let m equal to 2k squared plus k, which is an integer, then x squared is equal to 8 times m plus 1, where that m is definitely an integer. So that took care of the first case, and the second case is the 4k plus 3. All right, well, if x is equal to 4k plus 3, it's a very, very similar argument. We're going to square it, and we'll see that it's 16k squared plus 24k plus 9. And so what we want to be able to do is to write this as 8 times m plus 1. Now this one, I think y'all can see how to do it, but just kind of as a reminder, this might be on your scratch paper here, that we want to aim for that. Well, I think we can do that. We can write this as, let's factor out an 8, and I'm going to write that as 2k squared plus 3k. I'm going to write it as plus 1 and then plus 1, because we had a 9 over here, and we needed to get to something, an 8 times something plus 1. And then the same thing works. The closure property tells us that what's in parentheses is an integer. The closure property, 2k squared plus 3k plus 1 is indeed an integer. And so if we let m equal that, plus 3k plus 1, which is an integer, then x is equal to 8m plus 1, where m is that integer, and we've already said that, so we'll leave that there. And so to sort of recap here, our cases, case 1 was x equals 4k plus 1, and we saw that that worked. Case 2 was x equals 4k plus 3. We didn't have to consider 4k or 4k plus 2 because those were even, so we said we ruled those two out. And since it works for all the other cases, and that's the only possible ways that you can write it as 4k plus something, we've covered all of our integers. And so finally we'll just say, therefore, x squared has the form 8m plus 1 for some integer m. All right, and so we are done with this proof here.